Hi, I'm Sam Liu, and my presentation is going to be on multifunctional design of domain wall magnetic tunnel junction artificial synapses for accurate training of neural networks. The purpose of this talk will be to show that domain wall magnetic tunnel junction devices are great candidates for artificial synapses in hardware neural networks due to their unique magnetic characteristics, allowing them to be very tunable, giving them excellent characteristics for online learning. So why do we care about neural networks? Well, first of all, the memory wall is a major bottleneck in traditional von Neumann computing since compute and memory are separate from each other, so you need to send information back and forth. This is a bottleneck in tasks such as classification, interpolation, and regression, in which software neural networks typically excel. Neuromorphic computing seeks to alleviate this problem by using massively parallel in-memory operations along with analog memory elements to create efficient hardware implementations of artificial neural networks. Like their biological analogs, neuromorphic computing systems consist of two main building blocks. So first of all, there are neurons shown in the circles here. Neurons integrate the incoming signals, perform some activation, and output based on those signals. Now synapses connect the neurons, so they're the lines shown in this abstract diagram here, and they're required to be multi-weight and non-volatile. And the inset here is a circuit representation of what these synapses look like in a resistive crossbar array. So two other characteristics important for artificial synapses include linearity and symmetry. This is particularly for implementation of backpropagation, a stochastic gradient descent-based learning algorithm for supervised learning. Linearity indicates something shown by this black dashed line here, where the other curves represent the varying degrees of nonlinearity. For example, in this ramp here, you want the ramp to be as straight as possible without any of the curves found in this experimental data. Symmetry is also important, as shown in the black curve in this figure here. As you can see, as nonlinearity increases, the accuracy of the neural network sharply decreases for an asymmetric synapse, whereas a network with symmetric synapses is more resilient to this nonlinearity. Proposed memories such as RRAM and phase change memory have nonlinear asymmetric responses, so there's room for improvement in this area. So firstly, why magnetic materials and devices for neuromorphic computing? Firstly, they're non-volatile. They have high endurance, so they can be trained over and over again. They're radiation hard, so you can implement them in areas where energy efficient edge computing is important. They're back end of line compatible, which means they're compatible with existing CMOS processes, and they have complex tunable behaviors for new devices and systems. Here, shown in the figure, we have a domain wall magnetic tunnel junction device with lithographically defined notches. The weight of the synapse is effectively simulated by the location of the domain wall in the free ferromagnetic layer. You propagate this domain wall by applying a current through the left and right terminals, applying either spin transfer torque or spin orbit torque, depending on the existence of a heavy metal layer. And you read by applying a current through the out terminal through the MTJ stack. And so this device is characterized using finite temperature simulations in Numax 3. We include notches in our design to provide lithographically defined domain wall pinning sites. For example, they can prevent drift due to edge and temperature effects, as shown in this figure here, where if we spawn a domain wall at the edge of a track, it stays within a notch in the notched sample, and it drifts towards the center in the smooth sample, which is bad for memory applications. These notches must also be deep enough and spaced enough to prevent depinning. For example, DMI can cause unpredictable writes due to domain wall tilting, as seen here, where the domain wall tilts in and out of different notch positions, and as a result, this is unpredictable. And we want more reliability on that front. Notch definition can also promote linearity symmetry, as shown here, where the notch device, if we send a set current pulse every 5 nanoseconds, has a very repeatable and constant domain wall position change, while for the smooth one, it's nonlinear because it changes differently each time. We can characterize the linearity and symmetry by applying pulses to the domain wall in order to propagate it across the entire length of the track. For visual inspection, you can see that this ramp is extremely straight and also symmetric, which bodes good news. In order to quantify this, we can collapse them onto a single ramp with some standard deviation. And when we apply a fitting function and get the nonlinearity variable out, we can see that in this table, domain wall STT and domain wall SOT both perform very well with magnitude of nonlinearity below 1, which is very good. Cycle-to-cycle variation for domain wall SOT is higher at 3.23%, which is corroborated in this lookup table here, where it shows for both STT and SOT that the change in conductance as a function of conductance is very constant, so it means it's very linear for both of them. However, the larger noise is evident in the SOT 300K sample, but it will be shown later that this is actually a good thing. In order to evaluate the performance of the device in a neural network, we apply the device characteristics onto a crossbar architecture of these devices used in differential mode, which means that each synaptic weight, is represented by the difference in conductance of two of these devices. So one device represents the positive weight and one device represents the negative weight. Now the actual neural network consists of two layers, so it's 784 input units, 300 hidden units, and 10 output units. And this is implemented in cross-sim using the micromagnetics data we took earlier. We apply this on two tasks. First, the MNIST handwritten digits task, and secondly, fashion MNIST clothing articles task. So here are some neural network training results performed on the STT 300K synapse. And if we treat the number of levels as continuous, then we get something very close to the numeric value due to linearity, symmetry, and very low write noise. However, this is not physical since each notch gives a pinning site to the device, thus constraining the number of allowed levels in a device. So if we constrain that to 32 allowed levels or quantize it to 32 levels, then we get a very big performance decrease. However, this can be alleviated through periodic carry or using multiple devices for higher or lower significant bits, the scheme of which is shown here. And as you can see in the orange curve here, the performance more closely matches that of ideal, although it is still lower. So another way to alleviate these quantization effects is by taking advantage of the stochasticity I mentioned earlier for the SOT device. So for example, if you treat the weights as continuous, which is non-physical, STT outperforms SOT since the SOT has a much larger write noise. However, when you introduce 32 notches, so quantization to it, SOT far outperforms STT, as you can see in the bottom figure. This is because if you give a small update to the STT device, it'll be lost if it doesn't move the domain wall to the next notch. However, for SOT, since there is a finite chance that it moves the domain wall to the next notch, averaged over thousands of updates, this results in a higher resolution than the levels would dictate. This stochasticity can be modulated through perpendicular magnetic anisotropy and saturation magnetization, as well as spin Hall angle and DMI. So in summary, linearity and symmetry can be controlled using lithographically defined notches, and high performance can be obtained in training neural networks using stochastic gradient descent, indicating that domain wall MTJ synapses are excellent for deep online learning. This is accomplished by taking advantage of periodic carry and domain wall stochasticity to alleviate the problems that are accumulated due to quantization. So some future directions where we can take this work include exploration of optimal stochasticity for online learning and implementing unique synaptic functions through magnetic properties. So first of all, we can implement tunable second order plasticity or metaplasticity. Stay tuned for experimental results in talks given by my colleagues later. Short-term plasticity for neural network pruning, and stochasticity for Bayesian neural networks. Thanks.